Here we go, we're live. Let's start the slideshow from the beginning. There we go. The periodic table, it was first created by a scientist named Dmitry Mendeleev. So you can fill that in the blank there at the top. First created by Dmitry Mendeleev, and he organized the elements based on properties. He was the one who realized actually elements aren't completely random. They belong to families. And it was a brilliant insight. It took him a few years. He tried several different ways of organizing it before he kind of stumbled onto this table. And the reason we're so impressed, Kevin, is he left blanks in his periodic table saying, look, we haven't discovered an element there yet, but I'm telling you it exists. Go find it. And that was a gutsy thing to say to other scientists. Periodic table is arranged into families. You can fill in that blank if you haven't already. And those families all have common properties. We'll talk about what some of those properties are. Each element has its own box on the periodic table. And there is a tremendous amount of information in the box. So the first thing you have is the name and the symbol. I don't care which one you use in your notes. I will probably choose to use the symbol. Why? Because it's shorter, it's less writing, and I'm lazy. Also, it helps me reinforce what symbol goes with what name. If I write the symbol, but I think the name in my head, that's an easy way to help memorize what's going on. There is something called the atomic number. That goes in the next blank, which is the upper left corner. And that's the number of protons in that particular atom. So, on your periodic table right now, find element number, atomic number 8. What's atomic number 8? Oxygen. How many protons does oxygen have in its nucleus? 8. In fact, the number of protons is what determines what the element is. What element would you have if you had 53 protons in the nucleus? Go find it. If you have 53 protons in the nucleus, what element must it be? Iodine. Iodine? No. Yeah? Is it? Yeah, okay, yeah, that works. Okay. We can change the number of electrons pretty easily. In fact, you're going to find that's where all the action is. Radioactive elements change the number of neutrons, but if you change the number of protons, you no longer have iodine. It's something else. It's something else. So we have the atomic number, upper left corner. We also have the atomic mass. That's how heavy it is. That's the bottom row. That's the average mass of an atom. You'll find next year that we can change the mass in various circumstances, and that's why if you look at the atomic masses, many of them have decimals. What's the atomic mass of element? First of all, element number 43. Find element number 43. What is it? Sorry? Technetium or technetium, is that 43? Element 43? Okay. How many protons does element 43 have? 43. What's its mass?
7+.
No, the bottom number. 98. 98 even? Is it 98.0 or is it 98 even? If you look at some of the other masses, you'll notice they have decimals.
Yeah.
Usually that means they're radioactive. Okay, not always, but usually. And the radioactive element weighs slightly different, and that's why this is an average mass. You really don't need to know that, but I'm a nerd, I have to tell you. Then there is something called, and this is hugely important, the ion charge. That's the number in the upper right side. And ion charges can be positive or negative. So if you would be so kind as to find potassium, its symbol is a capital K. It's on the far left row somewhere. Find it on your periodic table.
19.
Element number 19. How many protons does potassium have? 19. What's its mass? 39.1. If I was doing math, I'd round it to 39 because that's an easier number to do math with. What's its ion charge? 1 positive, a plus sign. Move over one element. What's next to potassium? Calcium? What's its ion charge? 2 plus. Move over, what's its ion charge? 3 plus. There's a bit of a pattern. The elements on the left, the metals, form positive ion charges. Go look at, Phosphorus.
What number?
I don't know.
15.
It's capital P. 15? I bet you it has a negative ion charge. Is that correct?
Yeah.
Because it's on the right. And I'll bet you next to it is sulfur. I'll bet you that has a negative ion charge. Yeah? Okay. What about on the far right side, the very, very far right column? Those are special. They have.
Uno or whatever.
Well, don't worry about, by the way, some of the stuff on the bottom, a lot of what I'm teaching you as you move further down no longer works. So most of what I'm teaching you is technically wrong, but usually right. Okay? Next page.
How come
So here's an example. Here's calcium. What's its atomic number?
40 point, or no, 45.
What's its atomic number?
20.
20. How many protons does it have? 20. What's its mass?
40.
40.1.
40.
I'd use 40. When it forms an ion, and we'll talk about how that works, it ends up having 2 positive charges, 2 plus. You had a question. How come?
Oh, how come number 117 doesn't have a mass?
Hasn't been weighed yet. Most of those ones down there literally exist for trillionths of a second or less. They're very tough to get their measurements. In fact, I think we proved last year, we actually got element 120. We confirmed that it exists, but we don't know much about it. We just confirmed that it was there, but we haven't had a chance to get its mass or its ion or any of that stuff.
There's no 120.
No, it's not on this, because this periodic table is already out of date. Okay. Well, and you'll notice the one back there, which is about 15 years old, has gaps. They knew there was an element 113 that existed, but it hadn't been created in a lab yet. We just knew it was there. And that's also the beauty of the periodic table. It allowed us to predict where we were going to be looking for something. We'll talk about how we did that. The atomic number. So this is back to our notes, I think, where it says atomic number. The atomic number is the number of protons in all atoms of that type. If the number of protons changed, it would now be a different type of atom.
So they're both protons.
So, for example,
Both spaces or
both what?
spaces?
Both spaces.
Like, spaces. Are you right?
Oh, sure, both blanks?
Yeah.
Yep. Okay. So what that means is all atoms with 6 protons are carbon. And all carbon atoms have 6 protons. If you have something with 7 protons, it's not carbon. It's, what's after carbon? Nitrogen. It's how we define what an atom is. The number of protons is always the same in every element of that type. We can muck around with the electrons, you'll learn that later. We can muck around with the neutrons, you'll learn that later. But the protons is what defines what an element is. It's always a whole number. You can't have half a proton. And then I wrote here, what's the pattern? As you move further down, as you move to the next element, what happens to the atomic number? It goes up by? So find element number 12. What is element number 12? Magnesium. What's its atomic number? 12. How many protons? No, how many protons? 12. Scooch to the next one. What's the element after it? Aluminum, which is element number 13. What I want you to notice, and maybe this is too obvious, it goes up by 1. If you move along the periodic table, every time you move over one spot, it goes up by 1. And this was how we started to realize that we were missing some elements. We said, oh, I've got an element and I can weigh it, and I figured out that it's got 29 protons. I've got an element here with 27 protons. You know what? There's probably one that fits in between. This was part of what helped when Mendeleev invented or designed the periodic table. We started being able to predict what we hadn't discovered yet. So what's the pattern? Will we discover any more elements? Maybe, but if we do, where will they be? In the middle of your periodic table? No. Where's the only spot we have room to add stuff? If we're going up by ones, where's the only spot we have room to add stuff? At the bottom. So if you saw Iron Man 2, that garbage where suddenly Tony Stark discovered a new element that was somewhere in the middle. No! No! We have them all. You can't have half a proton. That Iron Man 2 part there was garbage, if you remember the movie. He discovered a new element to replace whatever was giving him radiation poisoning in his chest. No! Impossible. Can't be done. I know. But I'll call out bad science. Atomic mass, next blank, is the average mass of an atom. No, but I put it there so it stood out. It's the average mass of an atom. That's why sometimes you'll see decimals. So for example, if you look at the atomic mass of, chlorine, find chlorine. Yeah, it's what you put in a pool. It's on the right-hand side of your periodic table.
17.
Element 17, what's its mass? 35.5. If I was doing arithmetic, I'd round it to 36, but actually some of the chlorine atoms have a lighter mass because they're slightly radioactive. Okay. The number of protons never changes. So how could the masses of two atoms of the same element be different? I wrote down hint. What else contributes to the mass of an atom? That can change. And we'll talk about how you figure out the number of neutrons. That's actually hidden on your periodic table somewhere, but you have to do some arithmetic, which is why if you want to, for the next few classes, you might want to bring a cheap calculator. It doesn't have to be a good one. All it has to be able to do is add, subtract, multiply, and divide. If you have one of those old solar free calculators sitting in a desk drawer at home somewhere, bring it here. Keep your good calculator for math. Yep. Nope. It's too easy to cheat. Sorry. Phones are not calculators. I wish I could, but it's too easy to cheat. Oh! It is the sum of the protons. I need to erase this, don't I, Mr. Dueck? Pen. Eraser. There. It's the sum of the protons and the neutrons in a nucleus. As the number of neutrons can change, this number is a decimal. What's the pattern? As you move to the right, what happens to the masses? Gets bigger, gets smaller, or stays the same? Goes up. Not always gets bigger. There is one exception. So for a candy, who can spot on their periodic table where there's one element when you move to the right, it's actually lighter than the element in front of it? Can you find it? I'll give you a hint. It's near the bottom. Tristan, element number what? Element 107, which is what? Element 107 is borium. Strangely, and this is where we're getting into really radioactive, really strange elements, it's lighter than the one in front of it. Okay? And this is why I said to you, Mitra, everything that I'm teaching you is technically wrong, but it's mostly right for the upper part of the periodic table where things behave properly. Okay? I'll get you your candy later. Ion charge. It turns out that atoms can gain or lose electrons. And when they do, they become charged, forming ions. We'll talk about how that works. If you gain electrons, because electrons are negative, if you gain electrons, you become more negative. If you lose electrons, you become positive. An atom walks into a bar and says to the bartender, "I've lost an electron." The bartender says to the atom, "Are you sure?" The atom says, "Yes, I'm positive." Tough audience. Tip your waitress. Okay. Some of you are still trying to figure that one out. It's okay. So, what's the pattern? On the left-hand side, on the metals, they lose electrons and they become positive. Do you see the ion charge in the top right corner of each square? They're pluses. Either just a plus for +1 or +2, and you're going to see some of them have more than one ion charge. We'll talk about that. Like I said, most of what I'm teaching you is technically wrong, but it's mostly right. On the left-hand side, the nonmetals, they want to gain electrons, which is why they have a negative charge. Oh, the fact that metals are willing to get rid of electrons, it's why they're conductive. It's why we build all of our wire out of metals, because they're happy to pass the electrons through the wires to the other end. So, metals, you can write this down, become positive. Non-metals become negative. You can write that down. That's a blank to fill in. And in the middle, it turns out some form more than one type of ion. What's the atom, what's the element that doesn't have a charge at all near the top row somewhere? Well, second row technically. Right above it. Carbon. Okay. The reason is carbon sitting where it is can either lose 4 electrons or gain 4 electrons. We'll talk about what makes carbon so special. There's a reason all of you are made mostly out of carbon. Carbon, it turns out, forms more compounds on its own than all the rest of the elements combined. So that's why we think if we're looking for alien life forms out there, they probably will be carbon-based, just because carbon forms all sorts of stuff. Worksheet, first section, page 20. I'm going to give that to you in a bit. Let's keep going. I forgot to include this in your notes. I apologize. So you need to write this down. You can probably put it right here. You got room? We need to talk about reactivity. It turns out, on the periodic table, the further down and the further out you go, the more boom you get. You want to write this down, and you want to put this, how about right there somewhere? Or you can put it all the way across. You got room at the bottom of the page. Well, you don't need to write down the I forgot part. Okay? So the rule. Yeah, on the back if you want. The rule is, the further down and out you move on the periodic table, the more chemically reactive the element will be. Write that down, and then we're going to answer these questions here. Write down this line here, and then we'll do these questions together. The further down and out you move, the more chemically reactive the element will be. And again, that's technically wrong. As you get further down, some of the rules change. Let me give you an example. Here's what I wrote. So, potassium is more or less reactive than lithium. On your periodic table, find the K. Where is it? Yeah, find it. Number 19. Find Li, lithium. Where is it? Just what's its, that's its mass. What's its number? Not 1. It's element 3, isn't it? 3. By the way, there's lots of numbers, and I'm going to be we got to keep them straight. So I'm pounding them into you right now. Potassium, is it below or above lithium? It's meant to be really obvious. Below, so it's more reactive. I can tell you that without doing the experiment, but I will show you some of the experiments and videos later on. It's really explosive, so I can't play with it, but I can show you videos of it blowing up. Okay? Find Mg on your periodic table. What number is it? What number is it? 12? And then find Na on your periodic table. Sodium is element number what? 11. Okay, so as you move downwards and as you move outwards, we're more reactive. So is magnesium more or less? Is sodium further out than magnesium? So sodium is more reactive. Magnesium is going to be less reactive. As you move out and down, you get bigger boom. Right? Since sodium is here and magnesium is right next to it, as you move outwards, you get a bigger boom. As you move downwards, you get a bigger boom. S. What's S? Sulfur. Is it more or less reactive than chlorine? Because it's towards the middle. It's going to be less reactive than chlorine. Chlorine is nasty, by the way. If you actually had chlorine poured on you, it's so desperate for electrons, it will rip them right from your skin. If you heard about in World War I mustard gas, which was used, that's what chlorine is. It literally melts your lungs, and it's disgusting. But it's also why it's such a good germ killer in water in pools, which is why we add a very, very tiny bit of chlorine to pools or to our water, and it kills germs very, very, because it rips the electrons from the germs and they die. Families. Families.
How about salt water?
Salt water? That works differently. I'll talk about it later. Families. Columns of elements on the periodic table have similar properties. In other words, can you all look up? Everything in this column is going to behave sort of similarly. Everything in this column is going to behave sort of similarly. Everything in this column is going to behave sort of similarly. We say that they are part of the same family. And there's certain families that you need to know, and they are on your table. The first one is the very first row. Can you look at the bottom right here? What's the very first left-hand family called? It's on your periodic table. What's it called? You need to look down, find it. What's it called? These are called the alkali metals. It's the leftmost column. It has lithium. What's right below it? Sodium. What's right below it? Potassium, rubidium, cesium, and francium. By the way, the further down you go, the more explosive and reactive they are. And I'll show you a video in a second. They are very, very reactive. And actually, for metals, they're very soft. You can actually cut them with a butter knife very easily. They're very, very soft. Put your pencils down. So, the one right next to them, next column over. This column right here. Alkaline. I think the names are stupid because we have alkali and alkaline. However, Mitra, you don't have to memorize it. At least they put it on there. Alkaline is this column here. These are called the earth metals. They're the second column from the left. One of their characteristics is when they burn, they give very, very specific bright colors. They're used in fireworks. They're used in fireworks. Put your pencils down. Look up. Back to the notes. From current slide. Halogens. That's the 17th column. That's this one second from the end, and it should say halogens at the bottom. Yes? So you don't have to memorize it, but you have to know that it's there. These are also very, very, very reactive. These ones, in fact, are corrosive. If they touched your skin, they would burn your skin quite substantially. Wait a minute, Mr. Dueck. I thought we put iodine on cuts. We put iodine mixed with another chemical, and the iodine is so corrosive it kills the germs because it's that corrosive. And we use chlorine in swimming pools because it kills the germs. Okay? And the very last column is the noble gases. They are non-reactive. These are the noble gases. Why are they non-reactive? We'll talk about why. But the reason they're called noble gases is the idea, you can imagine a king or a queen being very proper, like Queen Elizabeth, and never showing emotion. They're non-reactive, straight face. Pardon me? Yeah, rarely. Okay. I'll show you the videos in a second, but we'll finish the notes. I'm going to hand out the first part of the assignment, and then I'll show you these videos. Last line, note. Periods, or rows, go across the periodic table, and families, or groups, go up and down. So, BR, find BR, please, on your periodic table. What element number is BR? Not the mass, not the charge. What element number is BR? Pardon me? You guys don't have that in your notes? You don't have this. You can write this down if you want, or just watch. You may figure it out. So, okay, bromine, element number what? Okay, what row is it in? Count down very, very carefully. So bromine, element number 35, is in row 1, 2, 3. It's in row 4. Oh, sorry, yeah. Period 4, row 4 means the same thing. And family, as a number, it's family number 17, and family 17 has a special name. We call that the halogens. Helium, He, is in period what? What row is it in? Row 1, period 1. Family 18 as a number, and it's a noble gas. So when I talk about rows or periods, I mean horizontally, how far down we move. When I talk about families, I mean vertical columns. Got some videos to show you in a second. Couple of comments. Next class, you want to bring some pencil crayons. I'll have some, but I don't have 30 sets. So if you have pencil crayons, can you please bring some? And again, you probably want to start bringing a calculator with you. I got some videos to show you, but I got some homework to give you as well. So pause the video here.